Hello guys, welcome to Self-Help Maths Academy. So today I'm going to discuss about one of the important topic on the abstract algebra, that is the binary operation. So let's see what is binary operation is all about, and how do we actually deal with the examples on the binary operation. That is the discussion of today. So let's start now. Binary operation. So let's see what is the binary operation. So basically, binary operation, usually we denote it as dot or the star, or like say this symbol, or sometimes this symbol, or sometimes this symbol. These are some symbols with which we'll be denoting our binary operation. But actually, basically these operations, these symbols are very famous. So now let's see the binary operation which we defined with say dot or star, it on a non-empty set. We have to define them on the non-empty set. So it's a mapping. So it's a mapping from, say for example, if I consider a non-empty set A, then it's a mapping from A cross A to A. So when I take this A cross A, means I'm taking an ordered product. Like say, if I take an element AB, which is belongs to this A cross A, then there is some particular element, say P, which is belongs to this A. That means from the ordered pair to the specific number, it is a mapping. So mapping basically from A cross A to A. So in general, uniquely defined element, it is going to A. Okay. So for example, call it the product of A and B under the binary operation dot. Okay. So these are the symbols with which we'll be denoting our binary operation. So let's see some example for more clarity. So here, if I take an example, say, let me consider, let A be the set of rational numbers. If I'm considering this as the rational number. Okay. And then I'll be taking a mapping, say star is a mapping from A cross A to A. How do we define this? Say it is given by A star B equal to AB. You can see my binary operation is defined as the product of two rational number, because I'm taking the set of A as rational number. And we know the product of two rational number is again a rational number. So therefore, this will become a binary operation on a given set A. Okay, so now let's see another example where I take the ordinary addition. So if I take ordinary addition, this ordinary addition, if I'm considering, so which is say with a symbol, then this actually the number, these addition of these numbers, if you consider, then it is a binary operation on the set of real numbers, if you consider, or you take the set of integers, which you denoted by z also, or you can take it as the set of natural numbers. You take these sets, this will become the binary operation. For example, I take, say, I'm taking a binary operation on the set A, that is n cross n to n. That means, which is a star, where addition, this star is nothing but I'm taking considering the ordinary addition. So if I take an element, say 1, 3, which are belongs to the natural number set. So it's ordered pair which belongs to natural number set. When I take addition of these two numbers, so 1 plus 3, this gives me 4, which is again a natural number. So this indicates that the ordinary addition will become a binary operation on the natural number set. Similarly, it is the binary operation on the real number set and the set of integers. Now let's see, similarly, how do we actually talk about the ordinary multiplication? If I want to talk about the ordinary multiplication, so ordinary multiplication, if I consider, then this ordinary multiplication will become a binary operation on the set of real number, then on the set of rational numbers, and even the set of the complex numbers, and the set of all integers, and the set of all natural numbers. So this will become ordinary multiplication will become the binary operation on the all these sets. So for example, if you consider any two real numbers, say if I take any two real numbers, say 1.2 and 1.3, so you multiply these two, you'll be getting a new real number. Say if you multiply these two real numbers, 1.2 into 1.3, then I'll be getting the new real number, that is 1.56. So in this way, you can just take any real numbers which is belongs to again real number. So you take a product of any two numbers on this set, then it will be again belongs to that particular set. Therefore, ordinary multiplication will become a binary operation. So I was talking about here ordinary addition. So let me take a special case where it will not become a binary operation. So if I take, say, the specific case like set of odd integers, set of odd integer, or you can say odd integers or odd numbers if you take. I'll be taking odd integers if I take. Then if I add any two odd integers, let's for example 3 and 5. These are the odd integers which are belong to this odd number sets. But when I add them, 3 plus 5 will give me 8, which does not belong to the odd numbers. So that means if you take a specific cases like odd integers, then addition will not become a binary operation. So when we are defining the ordinary addition on the remaining set, when you take a specific case, it is not the binary operation. So that's how we should know where it is not becoming a binary operation. This indicates that not every operation which we are defining will become a binary operation. So if for example, let me say the specific case again here, like another operation like say ordinary subtraction, if I consider ordinary subtraction, if I consider what happens here. So ordinary subtraction, is it a binary operation on all the sets? If it is so, how? If it is not, then why? Let's see. If I take a natural number set specifically, first one. So you take any two natural numbers. So let me take now 2 and 3. Okay. So this belongs to the natural number set. But when I take a subtraction, 2 minus 3, this will be the negative one, which again does not belongs to n. But you can take 3 and 2. Obviously, it is 1 which belongs to n. But do you conclude by saying that this is the ordinary subtraction? No. If it fails at one particular number also, it is failed in general. So that means the ordinary subtraction will not become a binary operation on the natural number set, whereas it is the binary operation on the set of real numbers, on the set of rational numbers, on the set of integers, on the set of complex numbers, and so on, but not over the natural number. So this is like ordinary subtraction. Okay. And similarly, now let me take ordinary division. Ordinary division. So ordinary division, if I consider, then it will become a set of, the binary operation over all the non-zero real numbers, on the non-zero, say, rational numbers, and also the non-zero, what is it, complex numbers. And then it also becomes the binary operation on all these sets, like we can denote it as, say, R naught, Q naught. Then we can also denote it this as the C naught. So these are non-zero, excluding zeros. So if I take 0, then anything divided by 0 will become undefined. So hence we have to take the non-zero, real, rational, and the complex number set. Then it will become the binary operation. That ordinary division will become a binary operation. What about the other sets? Like for example, if you take a set of integers, so if you take any set, say 3, and say take 5, then you want to take the ordinary division. So this will be 3 by 5, where it does not belong to z. So therefore, on the set of integers and on natural number set, the ordinary division will not become the binary operation. Whereas if I take the real number set and rationals, even again, if I take the complete real number set, rational number set, and the complex number set, this ordinary division will not become the binary operation, whereas it is the binary operation only on the non-zero real numbers, rational numbers, and the complex numbers, which is very, very important to make a note of. Okay, so now let's see now some of the, like say, properties on the binary operation. What are the properties we should know on the binary operation? On the binary operation, let's see. So the first one is commutative property. We should know about the commutative property. Commutative. What is this commutative properties? So say a binary operation, if I take here any binary operation dot on over the set of, say, even given set A, this is the binary operation on the set A, then we say that the given binary operation is commutative when I take A dot B, which is equal to B dot A. This has to be true for all AB belongs to A. So if this is true, if A dot B and B dot A, they are one another same, this is true for all AB belongs to A, then we say that this binary operation is commutative. So first property. And the second property is a binary operation is said to be associative. Okay, so this binary operation dot on the given set A is said to be associative if I take, say, A dot B dot C is equal to A dot B dot C. So if this is true, then we say that the binary operation is associative. I also will take the examples. Don't worry, we'll be taking up examples on this. And then say, for example, here a set A has two binary operations, addition and multiplication. Okay, so if it is having addition and also the multiplication binary operation, then the multiplication is called, say, left distributive over addition. We call the multiplication is left distributive, left distributive over the addition, because I have both operations here on this particular set. Then it is denoted by A dot B plus C. So it is left distributive over the addition. Then this is nothing but A dot B plus A dot C. This is valid for all A, B, C coming from the given set A. And similarly, we can call the same as right distributive if it is B plus C dot A, which is equal to B dot A plus C dot A. Again, this is true for all ABC belongs to A. If that is the case, we call them as left distributive over the addition and left right distribution over the addition. Okay, so this is important. And then if the last one, an important one again. So there exists, say, three elements. If I take, there exist, say, A, B, C, which is belongs to A. Three elements on a given set A, and a binary operation. This I'm defining a binary operation over the set A again. Okay. Then left cancellation law holds. So there is something called left cancellation law. Left cancellation law holds if I take A dot B is equal to A dot C. So from the left cancellation law, this will give me B equal to C. This implies B equal to C. Similarly, I have got a right cancellation law. If you have got B dot A is equal to C dot A, this implies B equal to C. So therefore, we can have this left cancellation law and right cancellation law. So clearly we have got here the properties of the binary operation, commutative property and associative property. Then we have got the left distributive over addition, right distributive over addition, and left and the right cancellation law. So these are the important properties which we'll be using when we are solving the examples. Okay, so which is very again important. Now let's see some examples we will take and we will see whether they are binary operations or not. So let me take one example. Yeah. The example is, say, show that the binary operation, the binary operation, we are taking the binary operation, say dot or star, anything on the given set, on the set A, on the given set A of real numbers, which is defined as A dot B equal to 2A plus 3B. This is true for all AB belongs to R, is not associative, is not associative. So they ask us to show that the given binary operation is not associative. So what is given? Let's write solution for this. Given that the binary, this is the binary operation on the set, say let I consider A, B, C, which is coming from the set R, because it's a binary operation on a set of real numbers. How they have defined the binary operation? They have defined the binary operation as A dot B is equal to 2A plus 3B. Means the binary operation is defined as 2 times the first element plus 3 times the second element. Okay. So now let's see, in order to prove the associativity, we need to prove that A dot B dot C should be equal to A dot B dot C. This is what we have to prove. Now let's take one by one. I'll take the LHS first and then we will try to prove whether it is valid or not. Okay. So if I consider, say, A dot of B dot C. So let's take this. Now, in that, I need B dot C first, and then I'll consider this. So let B dot C will be equal to, since our binary operation is defined as if it is A dot B, then it is 2 times of A plus 3 times of B. Therefore, B dot C will be the 2 times of the first element. Here the first element is B plus 3 times of the second element. Here the second element is C, 3 times of C. Okay, so this is our B dot C. You can substitute back in this. This will become now A dot 2B plus 3C. Now you can consider this as one element. So now this is in the form of A dot, this whole thing if I consider as B, then it will be the 2 times of the first element. Here the first element is A. So 2 times of A plus 3 times of the second element. My second element is 2B plus 3C. So 3 times of 2B plus 3C. Okay. So this will give us 2A plus, if I multiply, this is 6B plus 9C. So let me consider this as, say, star. Okay. Similarly, now let me take the left hand side, right hand side, that is A dot B dot C. So in this case, I need A dot B. Already A dot B is defined, that is 2A plus 3B. I'm taking it. So 2A plus 3B dot C. Now this is our A and this is our B. Now this will be in the form of A dot, say, B. You can take 2 times of the first element. The first element is this 2A plus 3B and plus 3 times of the second element. So this is your second element. Now solve this. This is 4A plus 6B plus 3C. So let me take this as double star. When you see the star and double star, it is very much clear that they are not same. So here we have 2a, 6b, 9c. So here we have 4a, 6b, 3c. Hence, from star and double star, it is clear that a dot b dot c is not equal to a dot b dot c. Hence, the binary operation dot is not associative. It is not associative on the set of real numbers. So that's how we are supposed to define, solve the example. So let me take another example now, where we will be talking about, say, the binary operation. So if suppose, for example, I take, let dot be an operation. This is an operation on the set R, okay, of real numbers. Then it is defined as a dot b equal to a plus b minus 3. This is valid for all a b belongs to R. Okay, then the question is it commutative? Is the dot is commutative? The dot, is it commutative? Second one thing is the dot, the binary operation is associative. That's what we need to check. So they're asking us to check whether they're commutative or they're associative. So let's see what is given now. So given thing, if you see, they've given that there is a binary operation on the set of real numbers, and it is defined as, let me take this, a dot b is equal to a plus b minus 3 for all a b belongs to R. This is a binary operation which is defined on the given set. Okay, now for the commutative, for the first thing, to prove it as commutative, we know we have to prove a dot b is equal to b dot a for all a b belongs to R. This is what we have to prove. So let us take this one first, a dot b, which is already defined by the binary operation. It is defined as the first element and the second element minus, we have to subtract it by 3. So therefore it is a plus b minus 3. Let me take this as, say, star. And when I take now b dot a, so b dot a will be, since you can take the first element here is b, so b plus a minus 3. So you know that whether you add a to b or b to a, you'll get the same element. It's the same thing, because addition is commutative. And then we have got subtraction of 3. So if you take star and double star, it is clear that a dot b and b dot a, they are same. Hence it is commutative. I can write a dot b equal to b dot a. Hence our dot is commutative. Hence the dot is commutative. We can say this. Okay, now let's similarly we can check it for associative. Let's see whether it is associative or not now. To check for associative, now I'll consider all the three elements now. Say for example, if a, b, c I'm considering from the set of real numbers, then we should check a dot b dot c equal to a dot b dot c or not. This is what we have to check. Okay, then let's take the first one, a dot b dot c. So this will be equal to, for this we need first b dot c. So let's find that b dot c will be equal to, as per the binary operation, it is the first element plus the second element minus 3. Okay, so let's add it here. So a dot b plus c minus 3. Now this is your first element and this is your second element. So if you do the binary operation, it will give you the first element plus the second element minus 3. So this will give you a plus b plus c. Negative 3 will become negative 6. So let me take this as now star. Okay. So now I'll take the left hand side of it, I mean the right hand side of it, that is A dot B dot C is equal to. So A dot B, this is already defined. So let me take this as now A plus B minus 3 and dot C as it is. So now this is the first element. I can write first element plus the second element minus 3. Now just simplification, it is A plus B plus C minus 3 will become minus 6. So let us take this as double star. So from star and double star, it is clear they are same. So hence A dot B dot C is equal to A dot B dot C. Therefore, the star operation or dot operation will become associative. Okay, so in this way we'll be solving. Some more examples in our next video. We'll come up with now like some different varieties of examples where whether the given defined binary operation will become commutative or it's associative or not, and sometimes it become associative, sometimes it is not. And also we will see on some set it is satisfied, some set it is not satisfying. And then we will also see the how do we actually define the identity element with respect to the binary operation, then how do we define the inverse element in the binary operation. All that discussion we'll be doing in the next video. Okay, so in this video please see all this discussion, and get back to me if you have any doubts and any questions. Thank you so much. See you all in the next video, guys. Take care.